Hello, and welcome to Acoustics Derivations. In this video, we'll be talking about intensity. So, intensity, which is also known as acoustic energy flux, is defined as the time average of energy flow, where energy flow means energy per unit time, aka power, through a unit area where the normal to the area points in a specified direction. So intensity, sound intensity is specified in a particular direction. And we note that as capital I with a vector. Now, we can calculate intensity if we start or so with the definition. So it's the time average of power over area. So we'll write time average, and that's what those brackets mean, over area. Again, the brackets mean time average. Now, we can write power in terms of a force times a velocity over over an area, which then force over area is pressure. So we have the time average of pressure times velocity. And if we put that into our notation in acoustics, that is P times U, where, of course, U is a vector, and that's why we have that I is a vector. And so what does time average mean? Well, it's if we're taking the time average of some function f of t, that is equal to 1 over t av times the integral from 0 to t av f dt. Where t av is so if we're thinking of intensity, now suppose that we're looking in scalar form. So that's just P times U. So that's 1 over T av, 0 to T av, P U dt. Now here, T av is so if you're looking at a periodic wave, T av is the period of that wave. If you're looking at a transient signal, T av is the duration of said transient signal. And if you're looking at non-periodic waves such as noise, you let T av be some really long time such that you're essentially taking, T av goes to infinity. So you want a really long time. So let's now calculate the intensity of a plane wave. So you might recall, or you might know, that for a plane wave, pressure is equal to rho naught C naught U. So pressure is equal to density times the speed of sound times particle velocity. So when we take, when we take intensity, we're taking the time average of P times U, which is, well, so let's write U in terms of P. So it's U is equal to P over rho naught C naught. So our intensity is P squared over rho naught C naught. Well, the rho naught and C naught don't depend on time, so they can come out of the time average, like so. And now we'll say that this is actually equal to PRMS over rho naught C naught. PRMS squared over rho naught C naught. Well, what is PRMS? Well, RMS stands for root mean squared, and PRMS is equal to the square root of the time average of P squared. So that's why we square it. PRMS squared. And this is equal to the square root of 1 over T av times the integral from 0 to T av P squared dt. So you can see root, mean, square, or I guess you would go backwards. It's square root mean, but we call it root mean square. So this here is the intensity of a plane wave. Now, that's nice and all, but acoustics, while we use plane waves often, quite often, there's other kinds of waves. So we want to consider just a general case. So let's do that. Let's consider a general case. Let's suppose we have two arbitrary functions, f and g, such that we can write f of t is f tilde, capital F tilde, e to the j omega t, where f tilde is a complex magnitude equal to f e to the j phi sub f. So you can see that that's complex. And we also note that the magnitude of f tilde is equal to f, and thus so we can write f of t is equal to f e to the j omega t plus phi f. Okay, and likewise we'll consider the second function g tilde, and we represent it the exact same way. I'm doing here. Now, if you recall, we want intensity is the time average of pressure times particle velocity. We're just considering two arbitrary functions here, which we will eventually call pressure and particle velocity. But for right now, just two arbitrary functions that we want to find the time average of F and G. Okay, well, we can simply plug that in. Well, we have time average F times G e to the j omega t plus phi f e to the j omega t plus phi g. We note that f g e to the j phi sub f and e to the j phi sub g don't depend on time. So we have f times g e to the j phi f plus phi g times the time average of e to the j 2 omega t. Now, that's all good and all, except not, because the time average of e to the j 2 omega t, and I'll let you calculate this for yourself, is actually 0. So the time average of f times g, we calculated to be 0. Well, that's clearly incorrect. So what went wrong? Well, if it helps to think in terms of physical quantities. So if we think of F and G as pressure and particle velocity, the actual values of pressure and particle velocity are either the real components or the imaginary components of the complex form of pressure and particle velocity. Thus, those values, either the real or imaginary components, must be used when calculating the time average of the product between them. So you must use only the real part or the imaginary part of pressure and particle velocity. And I want to stress that, must use that, or you'll get 0 as you see here. So, okay, well, let's do that then. Let's just take the real part of F and G here. So we want to take the time average of the real part of f times the real part of g. So let's plug, lowercase g. So let's plug that in. So what is f and g? So we have the real part, so we have f times g, so those are real numbers, times the real component of e to the j omega t plus phi f, times the real component of e to the j omega t, omega t plus phi g. So there we go. Well, if we recall that e to the j theta can be written as cosine theta plus j sine theta, right? We can say that the real part of f and g, well, first of all, we can move f and g outside. So f and g move outside. And that is cosine omega t plus phi f times cosine omega t plus phi g. Okay, well, now we recall our trig identity that cosine theta, cosine phi, let me not use phi to not confuse here, cosine psi is equal to cosine theta plus psi plus cosine theta minus psi over 2. So we have that the time average of the real components is f times g times the time average of cosine, the 2 moves outside as well because it doesn't depend on time. The time average, so cosine 2 omega t, excuse me, plus phi f plus phi g plus cosine of phi f minus phi g. Well, it turns out that once again, the time average is 0. So 0 for the time average. Just like we had up here, a similar math. However, here we have 2 phase terms, phi f and phi g, but those don't factor into the time average because if you're taking a periodic signal and you want the time average of it, which we have here, we're looking at periodic signals because we have e to the j omega t for f and g. It doesn't matter where you start on your cycle due to the arbitrary phase terms phi f and phi g. So you have cosine 2 omega essentially, and the time average of cosine 2 omega, and I encourage you to do this, is 0. So with the arbitrary phase terms phi f and phi g, the time average is still 0. Well, okay, so that term goes away because it's 0, and this term turns out to not depend on time. Not depend on time. Okay, well, then that can come out of the time average. So we just have 1/2 f times g times cosine phi f minus phi g. Okay, so lovely. Now we recognize once again that cosine is the real component of the complex exponential. So we have 1/2 f times g times the real component of e to the j phi f minus phi g. If we move f and g inside, we have 1/2, 1/2 real f e to the j phi sub f g e to the j, the negative j phi sub g, which, if you recall our definitions of f tilde and g tilde, This is equal to 1/2 real times F tilde times G tilde complex conjugate, because it's a minus there. Now, we could have done this the opposite way, and we would have obtained 1/2 real F tilde complex conjugate G tilde. Again, the star means the complex conjugate here. It turns out that if you want a non-zero, which you do, time average of two complex quantities, you have to take 1/2 real, for example, here, F G tilde, where F and G are complex amplitudes. Well, so why did we do all this? Well, now we're going to consider the case once again of pressure and particle velocity. So we're going to let pressure be some P, where I'm dropping the tilde now, e to the j omega t, and u be some u e to the j omega t. Again, where P and U are complex amplitudes, but I'm not writing the tilde anymore. Thus, the time average of P U is equal to 1/2 real P U star, which is equal to 1/2 real U, P star U. P star U. Okay? And it turns out, if you were to do the math, this is kind of a neat little aside, this is also equal to 1/4 P times U complex conjugate plus P complex conjugate U. And of course, we could make these vectors if we put a vector everywhere. So if you're not just considering motion in one direction, you could do that as well. Okay, so that's what we will use going forward to calculate intensity. So let's do it. So we found earlier the intensity of a plane wave. Now let's find the intensity of a spherical wave. Intensity of a spherical wave. So we know that intensity is equal to 1/2 real P U complex conjugate, okay? And we know that little p is for a spherical wave traveling outward. I should mention that we're traveling outward. A over R e to the j omega t minus kr. Now, we also know that if you're familiar or you saw the video on impedance, that pressure and particle velocity are related to impedance via this expression, P over U. And we know for a spherical wave that the intensity is rho naught C naught over 1 plus 1 over j k r. So we know that U is equal to P over Z, which is equal to P over rho naught C naught over 1 plus 1 over j k r. Now, this is a bit we don't want to work in this form when we're finding intensities, because we want the actual the complex amplitudes rather than the entire time-dependent function. So we note that capital P is A over R e to the negative j k r from right here, just picking off the complex amplitude portion. And if U and P are related via the impedance, actually, the complex amplitudes are also related, because if you look here, you're going to have an e to the j omega t on top, and if pressure is proportional to e to the j omega t, then so is particle velocity. So both of those e to the j omega t's are going to cancel. So really, what we're looking at here is the same thing as we're looking at down here, because since the complex amplitudes, or excuse me, the time-dependent components cancel. So this tells us that U is P over Z. where Z is the impedance of the spherical wave. Okay, well, we want U star though. So U complex conjugate is P complex conjugate over Z complex conjugate. Okay. Okay, so let's calculate then intensity. So intensity, once again, is 1/2 real P U star, which is 1/2 real P star over Z star. But if you know your complex analysis, a number times its complex conjugate is the square of the magnitude. So we can pull those outside. So it's magnitude P squared over 2 real 1 over Z. Okay, so what is 1 over Z? Well, that's 1 plus 1 over JKR over rho naught C naught. So 1 over Z complex conjugate is 1 minus 1 over JKR over rho naught C naught. So we have that intensity is equal to magnitude P squared over 2 times the real component of 1 minus 1 over JKR over rho naught C naught. Well, the only thing real here is the 1 over rho naught C naught, so that will come outside. So we have that the intensity is P squared over 2 rho naught C naught. Now, one final thing, we had that P complex conjugate was the magnitude of P squared. That, if you think about it, that's actually equal to the magnitude of our total field squared. So we can write intensity as P squared over 2 rho naught C naught. Then we can write that as PRMS squared. That's a terrible P. PRMS squared over rho naught C naught, where we recognize that PRMS is equal to A over root 2 for a sinusoid. Okay, so where A then would be the amplitude. So if you plug this in here, you will find you have P over 2, or magnitude P over 2. Because what's the magnitude of P? Well, that's just the amplitude, right? Now, I want to pause here and note one thing quick. Note this expression here, PRMS squared over rho naught C naught. Now, this happens to look, if I can scroll all the way back to it, a lot like the intensity of the plane wave. Now, it turns out that while this is the same, this expression up here is equal to rho naught C naught URMS squared. And you can do that by simply, instead of making this substitution here, make this substitution here. So you have rho naught C naught U time, or U squared, which would be the RMS of U. Down here, this does not equal rho naught C naught U RMS squared, because for a spherical wave, pressure and particle velocity are not related simply by rho naught C naught, but by rho naught C naught over 1 plus 1 over JKR. So I encourage you to redo this little calculation to find the intensity of a spherical wave in terms of particle velocity. Now, one final example before we close here. Let's look at the intensity of a plane standing wave. And we will represent a standing wave as a plane standing wave, I should say, as two plane waves traveling, two plane waves with equal amplitude traveling in opposite directions. So we have two plane waves, so a e to the j omega t minus kx minus, excuse me, plus a e to the j omega t plus kx. So you see they have the same magnitude, but they're traveling in opposite directions. And we can actually write this as a e to the j omega t e to the kx plus e to the minus kx, just like that, which then you might be able to see we can write as 2a cos kx, if you recall the definition of cosine in terms of complex exponentials. Okay, so for a plain standing wave, we don't have a convenient form of impedance relation, so we need to appeal to the momentum equation, which states, the linearized version states rho naught du, since we're looking at plane wave, it's not vectored, dt is equal to negative dp dx. Well, we know that if P is proportional to e to the j omega t, so does u need to be proportional to e to the j omega t. Let me rewrite that P a little bit better. Okay. Thus, u is equal to negative 1 over j omega rho naught dp dx. Now, we recognize that u and p still both depend on e to the j omega t. Thus, we can write this in terms of the complex exponentials, because by canceling the e to the j omega t's on both sides of the equation, so we have u is equal to negative 1 over j omega rho naught dp, capital P dx. And remember, capital U and P are complex amplitudes. Okay, so then the question is, well, what is dp dx? dp dx. Well, P was two capital. So sorry, this is e to the j omega t, such that P, and I apologize for this, is cos kx. So what's the derivative of capital P with respect to x? Well, it is negative 2ak sine kx, such that u is equal to 2ak over j omega rho naught sine kx. Okay, so we want intensity, which we remember is 1/2 real pu complex conjugate. So we plug these in. So we have 1/2 the real component of, what was P again? 2a cos kx, 2a cos kx. And then we have, I'm going to take the complex conjugate of this, 2ak over j omega rho naught sine kx. Now, this first term is purely real. This second term is purely imaginary. Thus, when you multiply a purely real and a purely imaginary number together, you're going to have a purely imaginary number, but we only want the real part. Thus, the intensity of a plane standing wave is actually 0, which is pretty neat. What this means, so remember what intensity is. It was a power per unit area, thus an energy flow per unit area. So what this means is that for a plane standing wave, there's no energy flowing. you have a wave traveling to the right and a wave traveling to the left. If you were to look at them both individually, you would see energy traveling to the right and energy traveling to the left. But because we're in a plane standing wave, so they're both traveling, the you can think of it as the energy moving to the right is canceled out by the energy moving to the left, and thus there's no power being, or there's no power in the wave. So that concludes this video. Thank you.